In this video, we consider peptides, which are the polymers that you get when amino acids link together to form a longer chain. This is somewhat similar to how polysaccharides form when monosaccharides are linked together. However, the proteins that you get out of long chains of amino acids linked together end up actually being much more important physiologically than polysaccharides are. And conversely, monosaccharides in the body are much more important than individual amino acids are. So when two amino acids are linked together, a molecule of water is formally lost. Okay, so the H bound to the nitrogen of one amino acid and the OH from the neighboring amino acid end up disappearing, and what is created in their place is an amide. Okay, so the amide bond between two amino acids in a peptide is sometimes called a peptide bond. So if you look at the examples up on the screen, we have alanine in the left-hand panel here. We have alanine being the left-handed amino acid and glycine being the right-hand amino acid. So the blue OH of alanine and one of the red H's of glycine are lost as a water, and you form an amide bond between the nitrogen of the glycine and the carbonyl group of the alanine. So as you can see from this diagram, linking together alanine and glycine can be done in two different ways. And the order matters. So alanine on the left and glycine on the right is a structural isomer of the other dipeptide depicted on the board, in which glycine is on the left and alanine is on the right. Okay, so these two molecules, ala-gly and gly-ala, are structural isomers of each other. So by convention, when we are naming a dipeptide, we always refer to amino acids in order from the N-terminal to the C-terminal. And just so that we're clear on all of this terminology, the N-terminal is the amino acid on one end of the chain that contains a free amine, contains an NH2 group. That nitrogen is not part of an amide. And then the C-terminal is the amino acid on the other end of the chain that contains a free carboxylic acid. Okay, so in this case, the case of this dipeptide, glycine, alanine, glycine is the N-terminus and alanine is the C-terminus. So the peptide bond that forms between two amino acids, peptide bonds are flat and planar. Okay, so think of the nitrogen as being sp2 hybridized with the lone pair in the p orbital. So all of these atoms in an amide that's depicted up here on the screen lie in the same plane. And this is due to the resonance form of the amide, in which there is a CN pi bond. Okay, so remember back to amides, we can have, so for amides and esters, there is a second resonance structure that I don't like very much, in which you put a positive charge on the carbon and a negative charge on the oxygen. But for amides, having a lone pair next to the cationic carbon gives us this third resonance structure, in which you have a CN double bond, and that resonance structure is about a 40% contributor to the resonance hybrid. So therefore, the pi bond character here is about 40%. As a result, there is restricted rotation about the CN bond. That doesn't mean that rotation doesn't exist at all. It means that there's a reasonable energy barrier between rotating about this bond of about 80 kilojoules per mole. So that's, if we assume that an ordinary covalent bond is about 400 kilojoules per mole, this is about 1/5 of the energy of an ordinary covalent bond. So you're not breaking a covalent bond when you do this rotation, but it is still restricted. That's still a reasonable energy barrier. So we talk about dipeptides here as having what we call an S-trans conformation and an S-cis conformation. They're not truly cis and trans because that's not really a pi bond, and these are conformations rather than diastereomers, but we still use this terminology. And the S-trans form is going to be more stable due to less steric crowding. The two ends of the peptide chain are further apart from each other than they are in the S-cis conformation. And then if we look at a peptide that is larger than that, you can see that you can have free rotation about the other sigma bonds, the carbonyl to carbon and nitrogen to carbon bond to the alpha carbon. It is just the peptide bonds for which there is restricted rotation. Okay, so what that does to the three-dimensional structure of longer peptides is that the R groups, the side chains of the amino acids, actually alternate as to which side of the peptide they are on. Are they on the top side or the bottom side? And if you have a peptide chain that's linear, their relative stereochemistries are also going to alternate, assuming all of your amino acids are L amino acids. So for one, you're going to have the R group going back. For the next one, you'll have the R group coming out towards you. For the dashes, you have the R group going back. For the wedges, you have the R group coming out towards you. Okay, so what does the formation of peptides do to acid-base properties? Well, once the amino acids are linked together to form a peptide, the only nitrogen in the main chain that is still basic is the N-terminus. Okay, recall that amides are not basic at all because of the same resonance that we talked about on the previous slide. So because all the rest of the nitrogens in the main chain are part of amides and not amines, they are not basic, and the chain overall is actually neutral. Now note that the side chains, the R groups on some of the amino acids, can still be basic if they contain a lysine, an arginine, or a histidine, and some of them can still be acidic if they contain an aspartic acid or a glutamic acid. So the last thing I want to cover in this lesson on peptides is their hydrolysis. So like any other amide, peptide bonds can be hydrolyzed, and you can do this chemically in the laboratory by heating them for extended periods of time in the presence of strong acid or strong base. Okay, so the dipeptide phenylalanine proline, if you treat this with sodium hydroxide, concentrated sodium hydroxide, boil it, heat it to reflux for a long time, you will end up with isolated phenylalanine and isolated proline, the two amino acids. Now, of course, if we're doing this reaction under basic conditions, the amino acids that you're going to get out are going to be negatively charged because we're at high pH. An example under acidic conditions, this is a tripeptide, aspartic acid, serine, valine. Again, you heat this in the presence of H3O+, and you get out free aspartic acid, serine, and valine. And since this is happening at low pH under acidic conditions, the amino acids that you get out in the end are going to be positively charged. Peptides can also be cleaved enzymatically, and the advantage of enzymatic cleavage is that the cleavage is selective. Okay, so for example, the digestive enzyme trypsin, rather than cleaving this peptide between every amino acid, only cleaves polypeptides on the C-terminal side of every lysine or arginine residue. Okay, so what I have drawn here is a 15 amino acid peptide, and if we take this 15 amino acid peptide starting from the N-terminus, you have phenylalanine, tyrosine, leucine, isoleucine, lysine. Okay, there's a lysine that's going to get cleaved with trypsin. So trypsin is going to cleave between the lysine and the methionine to give you fragment number 1. Now we have methionine, glycine, alanine, tryptophan, arginine. Trypsin cleaves to the right side of the arginine, which gives you fragment 2, and then the rest of the chain is leucine, alanine, alanine, threonine, there are no more lysines or arginines, so this isn't cleaved any further, and we just end up with the third fragment because that is the C-terminus of the peptide. Okay, so that's how peptides can be hydrolyzed. In the next video, we're actually going to talk about how peptides are synthesized in the laboratory, which is interesting both because of the fact that small peptides are still made in the laboratory, but secondly, there is some interesting chemistry that's involved here that reviews the use of protecting groups as well as the need for what we call activating